Assalamualaikum and good day everyone. My name is Fatin Syairah binti Yusuf and my group member is Nur Syahira binti Zurnaidi and Arun anak lelaki Selva. We gonna to present about heat convection. Firstly is introduction. The transfer of heat between two bodies via current of moving gas or fluid is known as a convective heat transfer. In free convection, warm air or water rises and is replaced by a cooler parcel of air or water as it moves away from the heat body. There are two types of convection, which is natural convection and forced convection. Forced convection removes heat from the body by forcing air or water to move over the body surface, as in wine or wine generate water current. Next is objective. First is to study the transfer of heat by convection both naturally and by force. Second is to determine the effect of fin addition on the heat transfer characteristic. We move to the next part, which is theory. Heat transfer refers to the movement of heat or thermal energy as a result of temperature difference as well as the following temperature distribution and variation. The exchange of momentum, energy and mass in the form of conduction, convection and radiation is the subject of transport phenomena research. Mathematical formula can be used to describe this process. Next is apparatus. In this experiment, we use fin, cylindrical and flat plate, and LS17004 FFC free and forced apparatus. Next is experiment procedure. Experiment 1 free convection. LS17004 FFCA level table is used to position at the free and forced convection apparatus. The 3-pin socket was then hooked into the main power supply, which is turned on. The power supply unit in front of the control panel was turned on. The desired test specimen was chosen. The form of the chosen test specimen was written down and used the appendix to figure out the size of test specimen. The test specimen is inserted into the plate heater. Use the wing nut that come into it and secure. The heater cable of the test specimen is attached to the heater socket on the back of control panel. Using the digital handheld temperature probe and meter, determine the initial temperature in the air duct by inserting the probe into the temperature point E. Then, the temperature probe is moved to the point D after reading the temperature at point E. By turning the power regulator, the power delivered is regulated to 50 watt. Every 5 minutes, measure the temperature at point D and record in the table. Repeat the experiment until you reach a steady state in which temperature reading point D is constant. Try the experiment again with a different test specimen. Before remove the preceding heat plate, make sure it completely cool. Calculate the film temperature based on the temperature result. Then using the thermophysical parameter of gas product provided in the atmospheric pressure table, extract all the association data. Next is the experiment 2, which is forced convection. The 3-pin plug is inserted into the main power supply, which then turn on. The power supply in front of control panel is turned on. The test specimen of choice was chosen. The form of the chosen test specimen was written down, then use the appendix to figure out the size of test specimen and then insert into the plate heater location. Using the digital handheld temperature probe and meter, determine the initial temperature in the air duct by inserting the probe into temperature point E. Make sure the fan is cooled down. Place the temperature probe at point D after reading the temperature at point E. Then turn on the fan. Set fan speed to 0.2 ms and the animator to the point E. By turning the power regulator, power supply is regulated to 100 watts. Take the temperature reading at point D every minute and record in the table. Then repeat the experiment until reach a steady state, at which time the temperature value at point D is constant. Then repeat the experiment with a different power source. Then try the experiment again with a different test specimen. Calculate and film temperature based on the temperature result. That's all from me. Thank you.
Assalamualaikum and hello. My name is Nur Syairah binti Zunaidi. My ID number is MA190X7. I will continue presentation for part result and calculation. Okay, this is the data for free convection. Next, the sample calculation for free convection. From the data, we calculate the film temperature, volumetric thermal expansion coefficient, Rayleigh number, Nusselt number, coefficient of convection heat transfer, and heat loss by convection. Okay, next, from the table that I have made, we can see the formula and calculation how to get the value. Okay, for this one, this is the value I took from the table A15 at 40 degrees Celsius. We repeat the same formula and step for the next power, which is for 50 volt, 75 volt and 100 volt. Okay, this is the simple calculation for free convection, power 50 watts. Next, power 75 watt. And lastly, for power 100 watt. Next, the data and graph for forced convection. This is the simple calculation for forced convection, air velocity at 0.2 meter per second. Okay, from the table, I have calculated the film temperature and volumetric thermal expansion coefficient. For this calculation, we use the same formula as step but different at the Reynolds number. For free convection, we use Rayleigh number, and for forced convection, we use Reynolds number. Okay, next Nusselt number is the same formula, coefficient of convection heat transfer, the same formula. And lastly, heat loss by convection is the same formula. And this is the simple calculation for air velocity 0.6 meter per second. Next, 0.9 meter per second. And lastly is 1.1 meter per second. I think that's all from me. Thank you.
Hello everyone, my name is Arun Salom, Ethics ID MA19205. Today I will be presenting about the discussion and conclusion. Let's take a look at the discussion. The first question asks us to discuss the variation of heat transfer in free convection mode for different powers. As you all know, convection is the process of transferring heat by large movements of water droplets such as gas and liquid. The initial heat transfer between the object and the liquid occurs through the conductor, but the large heat transfer occurs due to the fluid movement. There are two types of convection, which are convection natural and convection forced. Natural convection is produced by different densities of liquid due to the temperature difference such as rising air temperature. Global air circulation in local climates, including air, is due to heat transfer through convection. Next is discuss the effect of air velocity to heat transfer characteristics for the forced convection mode. Forced fluid movement or forced convection occurs under the influence of some external agent such as wind, pump, and stirring fan. Forced convection depends on the type and physical properties of the fluid, its temperature, flow speed, shape, and the size of passage where the forced flow of the liquid occurs. The relationship between the area-specific convection heat loss (WOM²) and the air velocity in the range of 0.3 to 1.05 meter per second was described by y equals to 56.5 plus 16.9 log x at an air temperature of 20 degrees Celsius. For the convective heat loss of 30 degrees Celsius, this is linearly with air velocity y equals to 11.8 plus 40.1x. The third question requires us to indicate the difference between laminar and turbulent flows. Moreover, elaborate which one has the highest heat transfer coefficient. Laminar flow is a smooth and streamlined, while turbulent flow is irregular and chaotic. Low Reynolds number indicate laminar flow and high Reynolds number indicate turbulence. The behavior changes significantly in the case of laminar flow compared to turbulent flow. In complex processes, the analysis of laminar and turbulent flow is essential for efficient operation. In a turbulent situation, the increase in the rate of heat transfer is greater than in a laminar flow situation. This is because the number of Reynolds levers increase further during the crisis. The turbulence effect becomes more important as the second stream of higher Reynolds number. Let's take a look at the first question, which is discuss the effect of convection mode on the efficiency. The main advantage of force over natural convection is that it increases heat transfer. Since more fluid can move through the system at the same time, more heat from the fluid can be expelled from the heat source. In liquids such as water and air, convection is a more efficient way to convert energy. This difference in performance results in a big difference in time it takes to melt the ice. In both cases, convection works, but transmits less heat than convection. Discuss the effect of extended surfaces on the heat convection. Extended surfaces, also called fins, are generally used to improve the rate of convective heat transfer between an object and the surrounding water. Extended surfaces of fins are used to facilitate heat transfer due to the increased cross-sectional area where the convection process takes place. The fin material should be thermally conductive to the appropriate temperature gradient from bottom to top. Fins come in a variety of shapes and sizes, including pin fins, straight fins, ring fins, and more. Another important factor is the length of fin. We know that the length of fin is proportional to its length. On the other hand, since the temperature drop along the fin is exponential, it takes time to reach room temperature. It does not cause heat transfer over this length. There is no need to lengthen the fins due to waste, increased size and weight, and increased cost. The sixth question asks us to discuss the results we obtained during the experiment. The first experiment is a free convection. We determine the coefficient of convection heat transfer, which is noted by H, and heat loss by convection, which is noted by Q, in this experiment. We use 4 different power supplies for experiment 1, which are 25, 50, 75, and 100 watt. We achieved a convection heat transfer coefficient of H equal to 52.771 and heat loss of Q, which is 0.00787 for 25 watt. We found H equal to 58.497 and Q equal to 0.01334 for 50 watt power supply. For 75 watt power supply, we calculated H equals to 60.312 and Q equals to 0.0168. Lastly, we got H equal to 63.738 and Q equals to 0.0226 for 100 watt power supply. Forced convection is the second experiment. We used the 100 watt power supply and varied the air velocity in this experiment. We utilized 4 different air velocities, which are 0.2, 0.6, 0.9 and 1.1 meter per second, to determine the coefficient of convection, heat transfer, and the heat loss by convection, just like we did in the experiment 1. For a velocity of 0.2 meter per second, we achieved the convection heat transfer coefficient of H equals to 29.86 and heat loss of Q, which is 0.0143. For 0.6 meter per second, the results were H equals to 51.77 and Q equals to 0.0256. On the other hand, for 0.9 meter per second, we determined H equal to 63.394 and Q equals to 0.0230. Finally, for 1.1 meter per second, we calculated H equals to 70.14 and Q equals to 0.02. Now let's take a look at the conclusion. First question is, draw your own conclusion based on the experimental data. In conclusion, in the case of free heat convection, it can be concluded that the convection heat transfer coefficient H and the heat loss due to the convection field increases with power supply. Convection behaves as a heating force when the wind speed increases. The convection heat transfer coefficient H and the temperature drop in the convection field both increases. Next is comment on the performance of free and forced steam conversion. From the graph below, we can calculate that the temperature at point B increases with time as the power supply increases. The thermal convection graph shows that the wind speed rises at 0.6 meter per second when the temperature reaches point B. However, at 0.6 meter per second wind speed, it shows a decrease. The last question is comment on the addition of extended surface for heat convection. We know that the fin length is proportional to the fin length. On the other hand, the decrease in the temperature of fin follows the expansion, which explains why it takes time to reach this temperature. Plus, this length does not lead to heat transfer. It is not effective to lengthen the fin due to wasted material, increased size and weight, and increased cost. That's all from us. Thank you.